Today, we're going to discuss the integral formulas for hyperbolic function. Okay, so the integral of hyperbolic sine of du is equal to hyperbolic cosine of u plus a constant. Then number two, the integral of the hyperbolic cosine of u du is equal to the hyperbolic sine of u plus cosine. Number three, so the integral of the square of hyperbolic secant u du is equal to the hyperbolic tangent of u plus a constant. And number four, we have the integral of the square of the hyperbolic cosecant u du is equal to the negative hyperbolic cotangent of u plus a constant. And number five, the integral of the hyperbolic secant of u times hyperbolic tangent of u du is equal to the negative hyperbolic secant of u plus a constant. And number six, the last formula, we have the integral of hyperbolic cosecant of u times hyperbolic cotangent of u du is equal to the negative hyperbolic cosecant of u plus a constant. So we will try to memorize and familiarize this formula as we go on with our exercises. Okay, next here I have the identities for hyperbolic function. Because sometimes as we solve for our integration of hyperbolic functions, we need sometimes to use the identities for hyperbolic function. So we have here the square of hyperbolic cosine of x minus the square of hyperbolic sine of x is equal to 1. Number two, the hyperbolic sine of 2x is equal to 2 times the hyperbolic sine of x times hyperbolic cosine of x. Number three, the hyperbolic cosine of 2x is equal to the square of the hyperbolic cosine of x plus the square of hyperbolic sine of x. Number four, the square of the hyperbolic cosine of x is equal to the hyperbolic cosine of 2x plus 1 all over 2. And the square of hyperbolic sine of x is equal to the hyperbolic cosine of 2x minus 1 all over 2. And second to the last, we have the square of the hyperbolic tangent of x is equal to 1 minus the square of hyperbolic secant of x. And the last one, we have the square of the hyperbolic cotangent of x is equal to 1 plus the square of hyperbolic cosecant of x. And the next slide is about the definition of hyperbolic function in terms of exponential function. So I have number one, the hyperbolic sine of x is equal to e raised to x minus e raised to negative x all over 2. And hyperbolic cosine of x is equal to e raised to x plus e raised to the negative of x all over 2. And hyperbolic tangent of x is just a ratio of hyperbolic sine over cosine. So just a matter of substitution, you can have its definition. As well as the hyperbolic cosecant of x, we are going to apply the reciprocal identity. So it says that it is 1 over hyperbolic sine of x. So just a matter of taking the reciprocal for this, so we can have now its definition. And also for the hyperbolic secant of x, we use the reciprocal identity, which is now 1 over hyperbolic cosine of x, which is now taking the reciprocal of hyperbolic cosine of x. So we have that definition. And for the hyperbolic cotangent of x, so we take also the reciprocal identity of cotangent. So that's why we have now 1 over hyperbolic tangent of x. So it's equal now to e raised to x plus e raised to negative x all over e raised to x minus e raised to the negative x, provided that x is not equal to 0. Okay, so let's start with the exercises. So number one is the integral of hyperbolic cotangent of 5x dx. Since there is no direct integration formula for hyperbolic cotangent of 5x dx, so I will take first the ratio identity. So I can rewrite that one now as the integral of hyperbolic cosine of 5x over hyperbolic sine of 5x dx. So from here, I'm going to let my u as hyperbolic sine of 5x, and then the derivative of hyperbolic sine of 5x is 5 hyperbolic cosine of 5x dx. Since hyperbolic cosine of 5x dx is visible in the given, then I'm going to divide both sides by 5. So we can write now du over 5 is equal to the hyperbolic cosine of 5x dx. So we're writing now the given in terms of u and du. So the hyperbolic cosine of 5x dx can be written as du over 5 all over u. So we can now have, I can write now the 1/5 as the coefficient factor of 1/5 times du over u. And that is now 1/5 of ln of u plus a constant. So we're writing the given. So I can now write as 1/5 times ln of u now is hyperbolic sine of 5x plus a constant. Okay, for number 2, we have the integral of the square of hyperbolic sine of x dx. So in this case, we are going to use the identity of the square of hyperbolic sine of x dx. So the identity now of the integrand is equal to hyperbolic cosine of 2x minus 1 all over 2 of dx. So I can remove the denominator of 2, writing here before the integrand. So I have now 1/2 the integral of hyperbolic cosine of 2x minus 1 dx. And then I'm going to separate the terms. So I can write now 1/2 the integral of hyperbolic cosine of 2x minus 1/2 times the integral of 1 dx or just dx. Now after that, so I forgot the dx here. So therefore, we can use the integration formula. So we have now 1/2. The integration now of the hyperbolic cosine of 2x dx is equal to 1/2 times the hyperbolic sine of 2x minus 1/2 of x plus a constant. So I can write now as 1/4 the hyperbolic sine of 2x minus 1/2 of x plus a constant. Okay, in number 3, we have the integral of number 3. So the integral of 4 e raised to x hyperbolic sine of x dx. So since I have e raised to x here as part of the given, then I'm going to rewrite the meaning of hyperbolic sine of x in terms of exponential function. So I can write now as the integral of 4 e raised to x times the definition now of hyperbolic sine of x in terms of exponential function. We can write now as e raised to x minus e raised to the negative x all over 2 of dx. So the numerical coefficient of 4 divided by 2 will give us the integral of 2, and then using distributive property, e raised to x times e raised to x minus e raised to the negative of x. So the first term now will give us e raised to the power of 2x. And then the second term, we have e raised to x times e raised to the power of negative x. We have now e raised to 0. Then I will put here a quantity to that because 2 is common for the two terms of dx. So simplifying further, so we can write now 2, the integral of e raised to 2x minus e raised to 0 means 1. So I can replace e raised to 0 is equal to 1 of dx. And I will write 2 outside the integral sign. So we can write now 2, the integral of e raised to 2x minus 1 of dx. And then let's integrate now. We have 2 times the integration of e raised to 2x is equal to 1/2 of e raised to 2x. And the integration of 1 dx is just x and then plus a constant. So multiplying by 2 outside, so we have here 2 times 1/2 is 1. Therefore, it is now e raised to 2x. And 2 times negative x, we have now negative 2x plus a constant. In number 4, we have the integral of 4 e raised to x hyperbolic sine of x dx evaluated from 0 to ln of 2. So without the intervals, so this is just the same to the example number 3. So we will just use now the answer of number 3 for integrating the integrand. So we can write here now as e raised to 2x minus 2x, and then this will be evaluated from 0 to ln of 2. To evaluate this one, we're going to use the fundamental theorem of calculus. So we have here e raised to 2x and then replace x by ln of 2. So I can write now e raised to 2 l times ln of 2 minus 2 times ln of 2. This is now for the f of b minus, I will use a bracket for to make it clear that this is now the value of f of b from the fundamental theorem of calculus minus the f of a, which is now using 0 as the lower interval. So we have e raised to 2 times 0 minus 2 times 0, and that is now for f of a. So simplifying this, so we can write now e raised to ln of 2 raised to the power of 2. And the second term, we have to use the power rule, so we can write now as ln of 2 raised to 2 using the power rule of logarithm minus, we have e raised to 2 times 0 is just equal to e raised to 0 minus 2 times 0 is 0. Therefore, we can now simplify this one as e raised to ln of 4 minus ln of 4 minus e raised to 0 is 1 minus 0 is just equal to 1. And then on the first term, we have e raised to ln of 4 that is now can be written as 4 because e raised to ln of 4 is, we can cancel the e and the ln because they are reciprocal to each other. So therefore, it gives us now 4 minus ln of 4 minus 1, or that is now equivalent to 4 minus 1 by combining like terms. We have 3 minus ln of 4, or by using your calculator that has an approximate value of 1.6137. Okay, for number 5, we have the integral of the square of the hyperbolic secant of x minus 1 half. So to avoid writing x minus 1 half, I will let first u is equal to x minus 1 half. And the derivative of that now will give you du is equal to 1 dx or just x. So rewriting the given, so we can write now the square of the hyperbolic secant of u du. And by using the formula, since there is a direct formula for integration of this given, so we can just write now as the hyperbolic tangent of u plus a constant. And rewriting again the meaning of u, so we have now the hyperbolic tangent of x minus 1 half plus a constant. Okay, number 6, the integral of hyperbolic secant of the square root of x times hyperbolic tangent of the square root of x all over the square root of x dx. So first, I'm going to write u as square root of x, and then du is equal to 1 over 2 square root of x dx. Comparing to our given, so dx can be solved as dx is equal to 2 square root of x du. But what's the meaning of square root of x? Replacing the meaning of square root of x in terms of u, so we have square root of x is equal to u, therefore this becomes now dx is equal to 2u du. Now, after that, we are going to rewrite the given in terms of u and du. So we can write now as hyperbolic secant of u times hyperbolic tangent of u all over the square root of x means u times the meaning of dx is 2u du. Okay, and then after that, we are going to simplify. We have 2u in the numerator, so I have now 2u divided by u, so we can cancel the u, so the remaining term there is 2 times the hyperbolic secant of u times hyperbolic tangent of u. So instead, I'm going now to write 2 as the coefficient factor or the constant multiplier, so 2 times the integral of hyperbolic secant of u times hyperbolic tangent of u and du, because this one is now cancelled and cancelled. Okay, so from there, we are going now to use the integration formula. Since the integrand has a direct integration, so we can now write as 2 times the integration now is equal to the negative hyperbolic secant of u plus a constant. So replacing the meaning of u, so times 2 here outside, so it becomes now negative 2 hyperbolic secant of square root of x plus a constant. For number 7, we have the integral of 2e raised to x hyperbolic cosine of x dx evaluated from negative ln of 4 to the negative ln of 2. So first of all, I'm going to rewrite the meaning of hyperbolic cosine of x in terms of exponential form. So we can write now as 2e raised to x, and then the meaning of hyperbolic cosine of x, we have e raised to x plus e raised to the negative of x all over 2, then dx, evaluated from negative ln of 4 to the negative of ln of 2. So by simplifying the integrand, 2 divided by 2 is 1. So I can just write now as e raised to x, but multiply to the binomial of e raised to x plus e raised to the power of negative x. So it will give us the integrand now of e raised to the power of 2x plus e raised to 0, and then of dx evaluated from negative ln of 4 to the negative ln of 2. Before we are going to evaluate, so let us write first the integration of this. So the integration now of e raised to 2x plus e raised to 0, that is now equal to 1 half of e raised to 2x, and e raised to 0 is just equal to 1. Then the integration of 1 dx is just x, so we have plus x, and this will be evaluated from negative ln of 4 to negative ln of 2. Now, before we are going to evaluate, let us rewrite the meaning of the negative ln of 2 by using the power rule in the natural logarithm. So the negative ln of 2 can be written as ln of 2 to the power of negative 1, and that is now equal to the ln of 1 half. While the other one, we have the negative of ln of 4 can be written as ln of 4 to the power of negative 1, or that is now ln of 1/4. Okay, so from there, we are now going to use the fundamental theorem of calculus. So our f of b now will give us, we have 1 half of e raised to 2 times the meaning of x. Now we have the negative ln of 2, but negative ln of 2 now can be written as ln of 1 half, and then plus x, that is now ln of 1 half. This is our f of b minus f of a. We have now 1 half of e raised to 2 times the negative ln of 4, which is now the meaning of that is ln of 1/4. So I can write now ln of 1/4 plus x now is ln of 1/4. Okay, and after that, simplify further. So we can write now as 1 half of e raised to, apply again the power rule of the natural logarithm. That is now ln of 1 half raised to 1 half, and that is now ln of 1/4 plus ln of 1 half minus, on the second term, we have here 1 half of e raised to 2 times ln of 1/4. So the exponent of e, which is 2 raised to ln of 1/4, can be written as ln of 1 over 16. 1 over 16 because the square of 1/4 is 1 over 16. So I will write now as 1 half of e raised to ln of 1 over 16 plus ln of 1/4. And then simplifying further, we can write now as 1 half times the e raised to ln. We can cancel the e raised to ln, so we just write here 1 half times 1/4 plus ln of 1/2 minus, in similar manner with the first term, we can also write here as 1/2 of 1 over 16 plus ln of 1/4. Now, simplifying further, we can write now 1/2 times 1/4, we have 1 over 8 plus ln of 1/2 minus 2 over 16 is, we have 1 over 32 minus ln of 1/4. So combining like terms, so 1/8 minus 1/32 is equal to 3 over 32, and ln of 1/2 minus ln of 1/4 according to the rules in the natural logarithm. So when the sign is minus, we are going to divide. So we can divide now ln of 1/2 divided by ln of 1/4, and so the quotient for that will give us the value of ln of 2. And therefore, the final answer now is 3 over 32 plus ln of 2. Okay, today we are going to discuss the integrals leading to inverse hyperbolic function. We have 5 formulas. So number 1 is the integral of du over the square root of a squared plus u squared is equal to the inverse hyperbolic sine of u over a plus a constant, provided that a is greater than 0. Number 2, the integral of du over the square root of u squared minus a squared is equal to the inverse hyperbolic cosine of u over a plus a constant, provided that u is greater than a and a is greater than 0, or a is less than u but a is greater than 0. For number 3, we have the integral of du over a squared minus u squared is equal to 1 over a of inverse hyperbolic tangent of u over a plus a constant, provided that u squared is less than a squared. And another equivalent for this given, we have 1 over a of inverse hyperbolic cotangent of u over a plus a constant, provided that u squared is greater than a. So in number 3, we have two answers. It depends on the value of u squared and a squared. Whether it is u squared is less than a squared or u squared is greater than a squared. So for number 4, we have the integral of du over u times the square root of a squared minus u squared is equal to the negative 1 over a of inverse hyperbolic secant of u over a plus a constant, provided that u is greater than 0 and u is less than a. For number 5, we have the integral of du over u times the square root of a squared plus u squared is equal to the negative of 1 over a inverse hyperbolic cosecant of the absolute value of u over a plus a constant, provided that u is not equal to 0 and a is greater than 0. So I have some exercises here in order for us to familiarize using that formula. This is just a continuation for our previous topic, so I just write here number 8. Okay, for number 8, we have the integral of 2 over the square root of 3 plus 4x squared dx. So first, I'm going to find the value of u squared and a squared from the denominator. So our u squared now is equal to 4x squared, then a squared is equal to 3. So it follows that u is equal to 2x and a is equal to the square root of 3. So finding the du, we have now equal to 2 dx. So I have dx in from the du and also have dx from the given. So I'll define dx as du over 2. Now rewriting the given, so I can write 2 over the square root of 3 now means a squared plus 4x squared means u squared, and dx stands for du over 2. So simplifying, we have 2 divided times 1/2, that is now equal to 1. So I can just write now as du over the square root of a squared plus u squared. So according to the formula we have here, so we are using now the formula number 1, which gives us the answer of the inverse hyperbolic sine of u over a plus a constant. So we have here, this is now equal to the inverse hyperbolic sine of u over a plus a constant. So we have the inverse hyperbolic sine of u, which is now 2x, and over a, which is now the square root of 3 plus a constant. For number 9, we have the integral of 1 over x times the square root of 9 minus 16x squared dx. So our u here is for 16x squared. U squared is equal to 16x squared, and a squared is equal to 9, and u here is equal to 4x, and a here is the square root of 9 is 3. And then solving for the derivative of u from u equals 4x, so we have 4 dx. So I have dx in the given, and then I divide 4, so we have now du over 4 is equal to dx. But in the denominator, we have x, so I'm going to define x from u equals 4x. Solving for x, so we can now write here x is equal to u over 4. Now, rewriting the given in terms of u and du, I can write now 1 over, the meaning of x now is u over 4 times the square root of 9 means a squared, and minus 16x squared means minus u squared. And then dx stands for du over 4. So I have here a numerator of 1/4, and we also have a denominator of 1/4 from u over 4. So 1/4 divided by 1/4 is just equal to 1. So I can simply write that one now as du over u times the square root of a squared minus u squared. Now, using the formula that is now in the formula number 4, we have u times the square root of a squared minus u squared. So the meaning of that is the negative of 1 over a inverse hyperbolic secant of u over a plus a constant. So replacing now the value of u and a, we have now negative 1 over a is 3. And then we have the inverse hyperbolic secant of u over a. We have u now is 4x and a is 3. So we have now 4x over 3 plus a constant. Okay, for number 10, we have the integral of 1 over x times the square root of 4 plus x squared dx. So in this case, our u squared is equal to x squared, and a squared is equal to 4. It follows that u is equal to x, and a now is equal to 2. Then take the derivative of u, so therefore du is equal to dx. So dx is visible in our given, so we can now rewrite the given in terms of u and du. So we have now 1 times dx just dx, and dx now becomes du over x means u, and then the square root of 4 means a squared plus x squared means u squared. So that is now very basic in our formula, that is equal to the negative 1 over a of inverse hyperbolic cosecant of u over a, then plus a constant. So just replacing the value of u and a, so we can now have the negative 1/2 inverse hyperbolic cosecant of u here is x over 2 plus a constant.